So let's have a look at another few examples. In this example, we have a sum of squares in the denominator. It's 2x squared and then 3 squared. So what we're going to do is we're going to apply a trig substitution. We're going to replace 2x. Now since it's a sum of squares in the denominator, we're going to use the tangent function. So that's going to be 3 tan theta. And differentiating both sides, well, that becomes a 2 dx, and this becomes a 3 secant squared x d theta. And how does the integrand simplify? Well, what we originally had was a 2x squared plus 9 in the denominator. 2x we replaced with a 3 tan theta. So that's plus 9. So we can factor out of 9 from each piece. That becomes a tan squared plus 1. And a tan squared plus 1 is a secant squared, using that identity on the previous page. So the denominator, what's inside the square of the denominator, can simplify right down to a 9 secant squared theta. So in this case, our integral becomes, well, we've got a dx, is 3/2 secant squared theta d theta, and the 2x squared plus 9 becomes a 9 secant squared theta all squared. So we can pull out the 3/2 all the way out front, and we've also got a 1/9 squared, and we've got a secant squared up top with a secant to the 4th in the bottom, so that becomes a 1/secant squared theta d theta. And the 9 squared can come out and cancels with part of the 3 to give us 1/2 times 27, or 1/54. And the secant squared theta we can write as cosine squared theta d theta. And so our original integral has now been converted to this new integral involving theta, and now it's just the antiderivative of a cosine square function. So we can now use our identity again. This is 1/2 plus 1/2 cos 2 theta d theta, and we can go ahead and anti-differentiate this thing. Notice we use the identity again. That sine 2 theta can be written as 2 sine theta cos theta, and that extra 2 that would have appeared using the identity allowed us to cancel a 2 off from the denominator, which leaves us with a 108 in front. Now at this stage we need to re-express everything back in terms of x again, so we're going to use our relationship between x and theta. Get our little right triangle drawn to get back in terms of x. So that's theta. What we have is that tan theta is 2x by 3. That's what this identity, or this relationship, tells us above. And what's tan of theta? Tan of theta is side opposite over adjacent, so we can have an opposite side of 2x and the adjacent side of being 3. And that means that the hypotenuse is then 2x squared plus 9. Or in other words, 4x squared plus 9 square rooted. So we're going to need to know sine theta and cos theta, because if we look at what our integrand involves, what our integral involves, our antiderivative involves sine, cosine, and theta. So first of all, we have that theta is arctan of 2x by 3. What is sine theta? So 2 times x over the square root of 4x squared plus 9. And cosine is 3 over square root of 4x squared plus 9. And so our solution is then 1/108 times arctan of 2x by 3 plus 1/108 times sine, which is 2x over square root 4x squared plus 9 times 3 over the square root of 4x squared plus 9, which becomes 1 over 108 arctan of 2x by 3, and this becomes 6 over 108, so that's 18 in the denominator, x over 4x squared plus 9, and then we've got our plus c still hanging on. And so there's our antiderivative. Let's have a look at the next example. So in this one we're looking at the antiderivative of the square root of x squared minus 25 over x dx. And here we're assuming that x is bigger than 5. So we're looking at the difference of squares. The variable appears in the first one, the constant in the second one. So the trig substitution we want to use will involve the identity of secant squared minus a constant squared, or minus 1 squared. And so that means we want to make the substitution x equals secant of theta. And so dx is then secant theta tan theta d theta. Oh, we have to be careful here because I forgot to put the 5 in front. Why do we need the 5 in front of the secant? Because we're ultimately trying to reduce this part of the integrand. And the substitution, when we stick a secant in here, we're going to be squaring it, and then we'd like to factor out the common factors to make this a 1. And so since there's a 5 squared here, I'd also like to have a 5 squared appeared there. So this becomes 5 of secant theta squared minus 25, or 5 squared. So I can factor out the 25 of each piece, pull it all the way out of the square root as a 5, and that's a secant squared theta minus 1. And so that becomes a 5 times the square root of tan squared theta. And again, similar to the idea we had with the sine function in the previous example, or the first example we did, was we should really specify what angle theta takes on in order for x to sweep out all the values bigger than 5. So as long as theta takes on values between 0 and pi by 2, then 5 times secant of theta will take on values bigger than 5, which is what our x is supposed to take on. And it just so happens that on this interval, when theta is between 0 and pi by 2, the tangent function is positive there. So when I square root the square of the tangent function, that's just itself. I don't have to worry about a negative sign cropping up. So putting all this back in terms of our original integral, we have that this becomes 5 tan theta. Denominator is 5 secant theta. And dx becomes 5 secant theta tan theta d theta, which we get some 5's canceling, we get a secant canceling, and we get the integral of 5 tan squared theta d theta, which we can then pull the 5 out front. Now we need to antidifferentiate tan squared. Maybe trying to think of an identity for this, much like we had with the cosine squared, we had an identity for that. Turns out that there's a nice way to do the antiderivative of tan squared, and that is to realize that tan squared can be written as secant squared theta minus 1 d theta, using the identity we've written down on the previous page. And we know the antiderivative of secant squared, the antiderivative of secant squared is tan theta. And the antiderivative of 1 is just theta. And so there's our antiderivative taken. We now need to re-express back in terms of x. We look at our little right triangle to get the relationship. What do we have? We have that secant theta is x over 5. Now secant theta is the reciprocal of cosine. Cosine is side adjacent over hypotenuse. So secant is hypotenuse over adjacent. So since it's x over 5, we can take x to be the hypotenuse and 5 to be the adjacent side. So this becomes then the square root of x squared minus 25 is that side. So now we've got all three sides labeled. Tan theta is opposite over adjacent, or square root of x squared minus 25 over 5. And we're also going to need to know what theta is, because that's present in the antiderivative. And so we could just use the expression for tangent and take its inverse. So arctan is 1/5 the square root of x squared minus 25, all square rooted. So using those two relationships, we then get that this is 5 times tan of theta. Tan of theta is 1/5 the square root, so actually that cancels with that 5 and just gives us the square root of x squared minus 25. Minus 5 times theta, so that's 5 arc tan of 1/5 square root of x squared minus 25, and a plus c on the end. And so there's our antiderivative.